Hey everybody, we're going to look at what are known as standard reduction potentials. Previously we looked at what galvanic cells are, and we didn't really talk about how to calculate the cell potential. We just talked about what cell potential was and the origins of it, and basically how to set up galvanic and voltaic cells. So what are standard reduction potentials? They're essentially a chart of voltages that have already been calculated and tabulated. So it's a bunch of half reactions. Again, why we wanted to talk about the half reactions at the beginning of the unit. So we're going to have a bunch of half reactions that are tabulated, and the half reactions that we're going to be looking at are reduction half reactions. And it's their potentials, basically, because they haven't been hooked up to anything yet, of what energy they can produce. So we typically use reduction potentials, and there's no list of standard oxidation potentials. So there's not two charts, there's only one. We use little notations down here to recommend the overall cell voltage, and this would represent the half cell for the reduction. What we're going to do is we're going to take those reduction half cells and combine them with oxidation ones. So where do you get the oxidation ones if there's no chart? Well, you should know that reduction is the gaining of electrons, so oxidation would be the loss of electrons. So you would just use the same chart, you just have to read it backwards. Okay, so let's take a look. Here's an example of a standard reduction potential. I'll give you one of these in class if you don't have it already. Here's your voltages, and these are your half reactions. These are not complete reactions because they have electrons already in them. Alright, so you probably have already seen this before, but anyway, the electrons are going to be added to fluorine. We know fluorine is very, very good at taking electrons and making an ion, hence why it has a very high voltage. The more positive the value, the more likely that substance will gain the electrons. So therefore, this is going to be the best reduction reaction. Okay, the best reduction reaction is at the bottom. Okay, best reduction. I wish we could use the terms oxidizing agent because that's what this is. It's a great oxidizing agent. Down here would be the best oxidation reaction. Now you have to look at this backwards for the oxidation reactions, because if fluorine were to lose electrons, it would produce fluorine and 2 electrons. It wouldn't be very good because that would reverse the sign notation. Remember from thermochem, we reverse the reaction, we reverse the sign notation. So that's not going to be everything we're going to use here because these are a little different, but that's true. So if I were to have lithium losing electrons, lithium metal, would be a positive 3, right? That would be the opposite. So lithium losing electrons to make lithium plus and becoming minus. Well, that's very good. Metals tend to do that. Metals are good at losing electrons because they're not very good at holding on to them. So it makes sense that the lithium is more likely to lose an electron than it will to gain electrons, hence why a negative voltage. So for the oxidation part of this, we would say that this is positive 3.05 volts. Okay? Alright, so those are your potentials. And notice in here you got your metals down here at the bottom, you got some non-metals up here at the top, and then other bigger reactions. Okay? And down here in the middle we have a 0 because that's our standard hydrogen electrode. So keep in mind these are always reduction reactions and not oxidation. You reverse them for the oxidation. Alright, so here's the standard hydrogen electrode. This is our reference one, so what they've done is they established that this is 0. So we have our hydrogen electrode. This is a good one to look at because it's got the gases in here with the positive symbol, or with the platinum. So you have hydrogen gas that's pumped in here, and when the hydrogen gas comes in contact with a metal, it's going to draw electrons over. So the electrons are lost by the zinc and attracted over here. You have a solution of nitric acid down here. The nitrate goes up here because of the transfer of electrons and all that we saw earlier, and you get a voltage. And this voltage is going to be for both cells, right? Both of them. But we're going to say that this one here is 0. So when we come back and do our calculation, we can say, okay, here's what we're doing. We're taking our oxidation and our reduction. Well, what's being oxidized? Let's go back and look. The electrons are being lost on this side, so this would be my anode, and this would be oxidation, loss of electrons. So therefore, we have oxidation here, reduction here. So the zinc is losing electrons, while the hydrogen is gaining the electrons. So we know that the overall voltage, right, we measured that in the lab, we know that that's the voltage, 0.76 volts. We're going to set this equal to our oxidation, reduction. Well, we know that we're going to set this one equal to 0, so we're saying that this is 0, so therefore the oxidation of zinc would be 0.76. Now remember, the chart is based on reductions, not on oxidation reactions. So therefore, we have to reverse the reaction. We want the zinc to not lose electrons, but the zinc to gain electrons. And we're going to take this reaction and rewrite it as a reduction potential, and therefore we would make it negative 0.76 volts. Okay, so the reductions are always going to be gaining electrons. And that's why zinc is on this chart at 0.76 negative, because it's down below. Why is it happening? Because everything above is going to cause the bottom ones to oxidize. So if you have one above, it's going to have to oxidize the one below. So keep that in mind as we're doing this. So if this reaction up here is very good at reducing, it's going to oxidize everything below. So if I put this together with this reaction here, I'm going to have to reverse this one so that the iodine is going to be, losing the electrons as opposed to gaining them, because fluorine's always going to take them. We'll talk more about that in class. Okay, so we can come back to our zinc-copper electrode. Remember, we had the zinc solid reacting with the copper ions to produce zinc ions and copper solid. Okay, well, for this reaction, the voltaic cell, we know the voltage was 1.1 volts. And therefore, if we know that the zinc one is now 0.76 negative, well, what's zinc doing? Zinc is going from 0 to positive 2, right? 0 to positive 2. Therefore, it's going through oxidation. So what we're going to want to do is reverse the sign notation on that and make that our oxidation reaction, because that's what's happening in this process, and this is going through reduction. So therefore, when we plug it into the equation, we're plugging in the 7.76 into the oxidation part. We can calculate the standard reduction potential for copper 2 plus to gain 2 electrons to become copper solid. Okay, that would be what would be listed on the standard reduction potential. So if we look at copper, copper is right here, so it's positive 0.34 based on that. Okay, and that's how they figured out that chart. That chart was figured out just by doing that with all of them. All right, one last thing, well, two things. I'm going to show you an example, but for one, when we combine standard reduction potentials like I was doing, there's a couple things to remember. If you use this equation, you have to remember to reverse the sign of the oxidation. I like this. I want you to know that. I want you to know that the oxidation reverses and you reverse the sign notation. So if you reverse the reaction, the sign of the potential must be reversed. Okay, so that's very good. Like, the book, I think, does something different. I don't know. I wouldn't use the book. I would use what I do because, better than the book. Anyway, number 3, standard reduction potentials are intensive. This is the one that everybody misses and screws up, because we did everything with thermodynamics, because heat is extensive. Electrical energy is intensive because it's joules per coulomb. We'll get to that a little later. So it doesn't depend on how much. What that means is if you multiply the reaction, you do not multiply the voltage. So do not multiply voltage. Okay, your cell voltage, your EMF. So if you double the reaction, you keep the voltage as is. Do not multiply its cell potential when you make that change. I'll show you an example. All right, so let's take a look. What we're doing here is we are going to calculate the cell potential, which is the EMF for the cell potential. That's what we're looking for here under standard conditions. Well, that's going to be the oxidation plus the reduction. Okay, so the oxidation plus the reduction. All right, so I need to look at the reaction. What this is a solution of nickel nitrate. The nitrates we don't care about. Those drop out. So really what we're looking at is nickel 2 plus ions and silver ions. Okay, nitrates drop out. They're not going to be that important. So what's happening here is that the silver is going from a 0 charge to a +1 charge. Nickel is going from +2 charge to a 0 charge. So what's undergoing reduction would be the nickel. Nickel is going to be gaining 2 electrons to become nickel 2, or nickel solid. We can figure out what the reduction for that is. And the silver is losing electrons. How do I know that? Because it's going from 0 to plus, so it has to lose electrons, and we can look up the oxidation for that. Okay, so we go to our chart, and we look up the 2 numbers. So you would find silver in here, and silver has a voltage of 0.8, and nickel is down here is a net voltage of 0.28. So let's go ahead and plug those numbers in. So my nickel was negative 0.28 for the voltage for the nickel. And if you go back on that chart, the voltage for this under reduction was positive, but now I'm going to make it negative 0.8 volts because I reversed it. I reversed the reaction. Now notice the electrons don't match up. I have to multiply this by 2 in order to get that to happen, but I will not double this. This is intensive. It's independent of how many times I do that. All right, so if I add these 2 reactions up, the electrons cancel. I end up with nickel 2 plus 2 silver gives me nickel and 2 silver ions. And when I do that, the overall cell potential is the sum of the two steps, so I'm going to end up with a negative 1.08 volts. Now the question is, will this process happen? If I take silver metal and I put it into a solution of nickel 2 nitrate, will the reaction happen? Is it spontaneous? Is it thermodynamically favorable? No, it is not. It's not going to happen. But if I take nickel solid and I put it into a solution of silver nitrate, the reverse reaction will happen because it's negative voltage. We want a positive voltage for it to be spontaneous or thermodynamically favorable. So what would the free energy be for this process? Positive. What would K be? Less than 1. Okay, guys, that's it for today. We'll kind of look at some stuff in class. See you later.